Yeah, we're good. Well, hopefully more people show up. How's it going, Joey? It's fair. Do you have your stuff here, or do you have to go get it like this weekend or something? Nice. Alright. No, not like this. Don't do me like this, lonely screen. Okay. Disconnect, reconnect. There we go. Should be good. No? My lonely screen shows this though. Oh, there we go. Man, that delay is long today. How long is that delay? That looked like more than 7 seconds. It's definitely more than 2 seconds. Yeah, that's probably about 7 or so. So once we actually start class, I'm gonna mute myself in Discord so that you don't like hear me talk before I write. But you guys can still ask questions in here, either via text or via voice. Everyone's leaving. It's not a good sign. That's not surprising. All right. Fun things. Domus, welcome. We have less than half of our class. Great sign. All right, well, it is 11 o'clock, so I'm going to go ahead and get started. Okay, so hopefully, maybe I will send another email. I thought it was pretty clear that we would be having class and people should check Discord in general, but I'll just send an email. Twitch.tv. You should be on both, Tyler. Yeah, I guess if everyone's just on Twitch, I guess that's fine. But if you want to ask questions, I mean, you can text them via Twitch chat. But I think a lot of the time it would be nicer if people just join the live stream on Discord and then ask me questions verbally. That's probably going to be quicker a lot of the time, unless I'm like on a roll and you want me to shut up and then just like put a text question. So now I'm going to wrong channel, Tyler. You should join the live stream one. I'm going to mute myself in Discord, and that way there's no lag with my writing coming 7 seconds after my voice. But you guys can still join the live stream in Discord, and you can just unmute yourself if you want to ask a question. Okay, but otherwise, to avoid background sound and feedback and stuff, just stay muted. Alright, let's go ahead and get started then. Okay, so we left off last time with 417 and 418, and basically what we're trying to do here is show, well, here, since I still want to wait, is there a link on Discord to go to? It's just our usual Discord. I sent it in that email, and I think that link never dies. Yeah, that also works. So maybe while I'm waiting for a few people to arrive, I'll talk a little bit more about logistics. So I'm going to post new office hours sometime today. So basically, I think the way that things are going to work with the Discord servers, I think it's best if I have class-specific office hours. And that way, there's something called going live. If you look next to like your hang up button, if you join like a voice channel, your disconnect thing, the thing to the left of it is to go live. And basically I can do what I'm doing on Twitch right now, except you wouldn't have a delay. The issue there is that it wouldn't record it, but that's fine because I don't want to record office hours. And so I can interact and share screen with you, and you could share screen with me too if you wanted to go live or do a direct call. And so I think that would be ideal for office hours. So these will come later today, and they will be class specific. And so I'll kind of plan on definitely like right before problem sets are usually due, right, like Fridays at 5. So I'll definitely do something like on a Friday, and then probably some more on maybe like Tuesday and Thursday. Calc has homework due every Monday, Wednesday, Friday, so I'll probably have hours for them all 3 of those days because I'm realistic. And then maybe topology will be more Tuesday, Thursday focused, and that way I can kind of hit everyone. Okay, so that's the plan there. And then the projects are posted, right? So that's an assignment up on Canvas, so you can scroll through those, read my little blurbs about the projects, think about what sounds interesting to you. If you're looking into things like Googling and are having trouble deciding between things or aren't exactly sure what a project would look like, feel free to just ask me. You can always like send me a direct message in Discord, or you can email me, whatever works. Okay. Any questions on stuff then before we get started? I'll have all the grading done here. I have everything set up now, and so now I'm ready to like catch up on grading. So it should be done by tomorrow, hopefully. Right, review session. I will put up a doodle poll right after class. So I'm thinking either tomorrow night or Friday night. But I'll put some other options in there. So I'll put probably something like 4 to 6, maybe like a 6 to 8, 7 to 9, 8 to 10, those kind of things, and see what works best. Okay. And then if you have nothing to do this weekend, I don't know how much social distancing you're truly practicing, but I'm probably going to stream some Hearthstone and not talk about math on Saturday if you just want to like join, hang out, throw some funny emotes up in the Twitch chat or whatever. you can feel free to come by or not. But yeah, I'm planning on streaming that. Once upon a time, I was good at the game, so might be fun, especially if you actually know Hearthstone. All right, so let's go ahead and get started then. So I am going to be uploading these notes, so just in case, I know some people are going to be coming by to pick things up if you haven't already moved out, and so if you are doing that on like a weekday, you can always use the Twitch recording together with the notes I upload to figure things out. But hopefully you can do that on a weekend and not miss class. But I understand that travel may be restricted or whatever, and you got to do what you got to do. But yeah, as always, just communicate with me and we can figure things out. Okay, so the goal here is, again, our order of an element G is defined to be the order of the cyclic subgroup generated by G. And our goal here with, in fact, the very next problem is that the order of G is also the minimum number such that G to the n is E, minimum positive number. Okay, and so last time, right, we did 417 and 418, and we basically showed that if this guy is finite, then there at least is some positive power that gets us to the identity. And then our goal is to show, okay, the order is really the minimum power such that that happens. All right, so we are ready for 419. So here we've got G as a group, and the subgroup generated by G is finite. And so if we here define n to be smallest positive number such that G to the n is E, then what we want to show is kind of what we've seen, right, when dealing with Rn, that we basically get r squared, r cubed up to r to the n minus 1, and then we cycle back around. And so we want to get E, G squared down to G to the n minus 1. And that it's really this set, they're all distinct, there are no repeats, and that's the group we get. Okay, so this is really, we need to show that they're actually these distinct elements, right? So last time we used the division algorithm to get this direction. Okay, so that was essentially part of 417. But if you don't remember, right, so anything in the subgroup generated by G is going to be some integer power, right? And then the idea is that G to the m can be written as G to the nq plus r, but then anything to the nth power is E, and so basically this cancels out, the nq cancels out because it's just E to some power, which is still E, and then we get just G to this remainder, where our remainder is indeed between 0 and n minus 1. Right, and so that gets us the containment going left to right. And so what we really need to show is just that all of these are distinct, and then that'll give us the other way. And that we actually get in elements, okay? Because we usually don't write sets, right? I'm not going to write like 1, 2, 2, 3, right? I would just write 1, 2, 3 because I'm not an insane person. And so because of that, we want to ensure that we really get all distinct elements here. So why are they all distinct? Well, I gave you a little hint on the actual assignment, right? I said you should try to do this, you should try to do this via contradiction. I was making sure I actually did give a hint on that one. I did, I'm not lying. So suppose they're not distinct, right? What would this mean? Well, this is very similar to what we saw in 417, right? This would mean that we have some repeat. And so in this case, who knows what the repeats are, but we know that, like, say, g to the I is g to the j. For some, we'll just say I less than j, and here we want to make sure these guys are really in our list, right? Okay. Well, what we're going to be contradicting is the fact that n is minimal, right? This is a key assumption. So I'm just going to go back up here. It's really that n is the smallest positive number. That's going to be the key to our contradiction. So in this case, right, if j is greater than I, then we can multiply by the inverse, and we get g to the j minus I has to be the identity. Well, what do we know about j minus I? J minus I is positive, and j minus I is less than n, right? Because j is already less than n. So this has to be true, and this is our contradiction, right? This contradicts n being the smallest positive integer such that g to the n is e. So this can't happen. Thus, they are all distinct. Okay. Any questions on that? So again, if you guys want, I mean, you can obviously use Twitch chat, you can use the text in Discord, but you can also hop in the live stream channel on Discord and actually just like unmute yourself and ask questions if you have them. I'd like to see more participation in general, maintain some level of interactivity. All right. Well, I guess we will move on then. Okay. So 420 is basically immediate from 419. Right, so 420 says that, again, we have G as a group and this guy is finite. Then the order of G, which is the number of elements in this subgroup, is exactly, speaking of Discord. Yeah, it was the same one. Okay, anyway. Is actually the smallest in such that greater than 0, such that g to the n is e. Well, we already showed this, right? Because we know now that if g is finite, then this guy is exactly e, g, down to g to the n minus 1. Well, how many elements are there? This is exactly n elements. And so it's order n, and we get the result just immediately from this. Okay. So basically 419 was all the work, and this was just a quick corollary. I thought it might be useful, so I didn't assign these just because we've already kind of talked about them, but it's at least for completion's sake, it should be very quick to talk about this. So the Cayley graph, mostly because we've already seen Rn and kind of figured out what's going on. Right, so the Cayley graph for a cyclic group, if it's finite, is going to give you an n-gon, right? So you kind of go g squared, g cubed, and then I'll just do ... dots, and like this vertex here would be g to the n minus 1, and then we loop back around, right? And so we've already seen this with Rn, and these guys behave exactly the same. Something that we're going to see here in a second, at least by the end of today, is that all of the finite cyclic groups are isomorphic to Rn for some n. Unless you're like 1 or 2 and we call it, just the trivial or S2. And then if you want to look at the Cayley table, Maybe you've seen patterns before when dealing with Rn, like R4's Cayley table, but maybe you didn't pay a ton of attention to it. But let's look at this. So we'll have like E, G, G squared, and then we get down to Gn minus 1. Okay, so these obviously just repeat themselves because that's how the identity works. But then what happens? So you get G squared here, then G cubed. Basically, we've just shifted everything up 1 power on this one, right? And then we go back to E, kind of cycles around from the first row. We just kind of moved everything left by 1. And then you move everything left by 1 again to get the next row. And you keep going down, and eventually, right, you get G to the n minus 1, E, G, and then down here would be G to the n minus 2. Now, what do we see here? Maybe you see the pattern along these like anti-diagonals. You can also see like these are all going to be G cubes. You know, the next one will be all G to the 4th. Along like your big long anti-diagonal would all be G to the n minus 1s. And then the same thing happens, right? Like these are all E's, these are all G's, and then you end up down here. So it's kind of a cool pattern, and it's something that you can like very quickly see when you just look at a Cayley table, if it's ordered in the right way, right? It's easy to tell if something is cyclic. Saying it's not cyclic is harder because maybe if I switch the 3rd row and 3rd column with the 5th row and 5th column, switch those elements, reorder, maybe now it does look like this. So as always, it's like easier to rule things in than rule things out when you're looking at a Cayley table, which is why we don't usually look at Cayley tables. But thought it was kind of cool. Okay. So for 23, I mean, this is something that we've kind of already talked about. It's not really anything new here, but it's basically a division algorithm, right? So in this, our general definition is, right, like G to the m, such that m is any integer. But now we're saying if G is finite, so say finite, then we're saying we only need these positive powers, right? That we get E, G down to G to the n minus 1. We don't use any negative powers. Why? So I think there are a couple ways to look at it. I mean, one, it's the division algorithm, right? We can always divide by a positive number and then ensure a positive remainder, because you just like go below the negative number and make sure you have a positive remainder there. And so basically, right, G to the m again is G to the n cubed plus r, but that just reduces to G to the r, and this r is non-negative, right? So we only need those. Another way to think about it is, let's go up to our Cayley graph here, right? If I want to find the inverse of G squared, well, I can say G to the minus 2 by going this way, or I can say it's G to the n minus 2 by going the long way around, right? And so in general, you can do this. So G to the j inverse is G to the n minus j, if j is one of the guys in your list. So if j is between 0 and n minus 1. Right, so it's basically just go clockwise, keep going clockwise instead of going counterclockwise. All right. So hopefully, having that picture, I think, helps. Which is another reason I wanted to talk briefly about the Cayley graph. So 424 introduces a new notation. I think I did mention this one day in class, but just to be clear, when I say the term like n divides k, that's fine. N divides k, this would mean, or I would write the notation like this, so these are the same thing. And what this, another way you could think of this is k is divisible by n. Right, it's just kind of focusing on the thing dividing in as opposed to the thing being divided up. Or k is a multiple of n. All of these are equivalent. So if I see n divides k, that means I'm going to write k is n times L for some integer L. Okay, so that's right. Yes, that is only true for finite cyclic groups. Right, and the key is you can't go back around if it's the integers, right? If we see the integers Cayley graph, right, it's just going to be going in both directions. And so if you have like -2, -1, 0, 1, 2, then, I mean, 2's inverse is -2, but you can't just like keep going in the positive direction and somehow loop back to -2, right? You have to go left, and so you have to use the negative powers. Yeah, good point. Yeah, so for this, again, if you're proving things with divisibility, it's usually best to turn it into this statement about like being a multiple of the other. So we'll do that here. So this one, 424 says we have some group G, element G, little g, of order n, and then g to the I equals g to the j, if and only if n divides I minus j. Okay, so I mean we have to go two directions here, right? So I think, you know, we can just get after them. Let's go left to right. So if we know g to the I is g to the j, then you should already know what's going to happen here, right? So I mean, and in this case, it doesn't really matter whether it's positive or negative, because I'm not trying to make a claim about a positive power. But you should translate this into like an I minus j power giving us e, right? So maybe I'll put parentheses. Okay, so this implies g to the I minus j is e. And also g to the j minus I is e. One of those is positive, but we don't really care. You know, take whatever, I minus j, use the division algorithm. It's going to be nq plus r, right? And again, r is between 0 and n minus 1. So we can ensure that is positive, and that's all that really matters. And so, what do we get from this? Well, n was smallest, and so r must be 0. Do we see why this is true? So if r was not 0, right, then g to the I minus j is g to the r. And so if r is positive, it's less than n. So if r is greater than 0 and r is less than n, then we contradict the minimality of n, right? We contradict n being the smallest. So that's why r must be equal to 0 here, so that we actually get no contradiction. Okay, well, if r equals 0, then I minus j is n times q. Well, that exactly says it's a multiple of n, right? So n divides I minus j. So that gives us that direction. Okay, so what about the other direction? This one's actually much easier. I'll go back to black here. okay, so in this case, we know that n divides I minus j, and we also know g to the n is e, right? So if I minus j is, say, n times q, for some q and z, I mean, we don't really care what it is, but it's n times something, right? Then g to the I minus j is equal to g to the nq, but that is e, right? Because it's g to the n to the q, and g to the n is e. So this is e. Well, if g to the I minus j is e, then you can just multiply by g to the j, right? And so g to the I equals g to the j, and that is what we started with, right? That's what we wanted to get to. So we would be done. Any questions on that one? You guys really can join the chat if you want. I don't know how well this is working for you. That's fair. Forward direction confuses me still. Okay. So is it more the r being smallest? Part? So I can try to figure out. Okay. Right. So are we good here? Right. So this is division algorithm. And we know that g to the n is the smallest. Why does n have to be the smallest? We assume it, right? So we assume that the order of g is n. I just don't get the division algorithm, how it fits in. Yeah, so the division algorithm is something that, yeah, you should get used to using, right? So the point is, right, we're talking about divisibility, right? So, I mean, we're talking about n being divisible by I minus j, or sorry, I minus j being divisible by n. So, I mean, that's kind of a statement about the division algorithm, right? If you can divide by something, then when you divide by it, you have remainder 0, right? So these are equivalent statements. And so that's why I'm employing the division algorithm here. I just want to see, okay, I'm going to divide by it. What's my remainder? If my remainder is 0, then I've shown what I want. So I go ahead and divide, and I get it in this form, nq plus r. So I have my remainder. Now my goal is, what is this remainder? Can I prove that it must be 0? Well, n is the smallest, and again, this is by definition of what we're given, right? We're given the fact that g is order n. So n is the smallest power, positive power, such that g to the n is e. And since g to the I equals g to the j, we know that g to the I minus j is e. So, again, if g to the I minus j had a positive remainder there, or sorry, if I minus j had a positive remainder there, then using the division algorithm, because g to the nq is e, because g to the n is e, then these guys are equal, right? This is, again, just like you cycled around your Cayley graph q times for the qn, and then you ended up at g to the r. So that's how we're getting this equality here. And the point is, right, if r is positive, then we have a smaller power than n that gets us to the identity. But that's not allowed, because n already was the smallest. Thus, r has to be 0. And since the remainder is 0, I minus j is divisible by n. Does that make more sense? If not, I would prefer, if possible, I know you have a mic, I'm pretty sure, then maybe hop in voice chat and let me know what's not making sense. Okay. Not seeing anything, so I guess I will move on. Okay. So the next part is, again, a very, very quick corollary. 425, it just follows almost immediately from 424, right? So here, again, we're assuming that the order of g is n, so n is the smallest positive power. And so we can just directly apply, right? So we know g to the I equals g to the j if and only if n divides I minus j from 424, because we're exactly in that environment. We have the same beginning assumption. So if g to the k is e, well, e is g to the 0, right? So it's, the empty word, right? So you get 0 appearances of the letter g. Then, well, from our previous statement, right, like here your I is k and your j is 0. And so I minus j is k. And so the fact that n divides I minus j implies directly that n divides k. And so we get what we want. Okay, so it's basically just seeing this, that you can rewrite e as g to the 0, and then it immediately follows from 424. If you're on a laptop, I mean, okay, yeah. Well, we should try to figure out how to use Discord as well, because I mean, I am going to be using Discord for most things, including office hours. But yeah, we can figure that out afterward. Why can't we say that g to the k equals g to the n? You can also say that. Sure. But then you're not really getting the same statement, right? So if you put, let me write that. So if you say g to the k equals g to the n, then with the I minus j thing, right, then you're getting the n divides k minus n. And yes, this is going to get you to what you want, but it would require one more step. You'd have to say like k minus n is nq, and then k is n plus nq, which is n times 1 plus q, and then you would get n divides k. So it's basically, it also works, it just takes a more indirect path. But yeah, either one of those guys works. Yes, I will be making comments on the homework, so now I have Canvas up on my iPad and stuff, and so I can use this pen and mark things up. So for sure, I will be making comments. Okay. So 426, we don't really need to talk about. We already know this, right? Rn is cyclic. It's generated by R, or R inverse, and sometimes many, many more things. It depends on what n is, right? So this was just kind of a statement because the next one is like a big classification statement, right? So the whole point with 427 is that because we know about these rotation groups, the point is these cyclic groups in general are all rotation groups up to isomorphism, right? And we only care about things up to isomorphism anyway, so we may as well just look at these rotation groups. So the statement here, or at least the way I wrote it, is if G is finite and cyclic, and let's just say, since it's cyclic, that it's generated by little g, then G is isomorphic to, and we'll just say that order of G is n as well. Then G is isomorphic to Rn if n is greater than or equal to 3, S2 if n is 2, and the trivial group if n is 1. Right, so like these are our only options. And so essentially we already know everything that we need to know about cyclic groups once we prove this. So we should show this, right? So I mean, it's a claim about an isomorphism. So we should create an isomorphism. And, you know, if G is equal to G and Rn is generated by R, I mean, what's the isomorphism that you thought up? Why don't you either, you know, put it in chat, someone come in voice chat, but what's the map if you want some phi from G to Rn, where we'll just do the n is greater than or equal to 3 case. How are you going to define phi? Yeah, I think maybe you meant lowercase. But yeah, so I mean, essentially, right, the things in here look like, well, may not, yeah, to the k, right? Yeah, exactly. So phi of G to the k is R to the k, right? You just match your generator with your generator, and then all the powers should be the same, right? That's kind of the point. All right. So let's see that this is an isomorphism. So realize first that we only need to define this for k between 0 and n minus 1, right? Otherwise we just wrap back around and we're getting repeats. So we may as well look at this. But it doesn't really matter. You can pretty much do it for anything. It's just that, again, you would be repeating things, right? If you're order 20, I mean, you could talk about G to the 27th, but you might as well just call it G to the 7th, right? But, okay, so let's do onto first. Okay, so let, say, y be in Rn. Well, then we know y equals R to the k for some k. And then, well, we know exactly what maps R to the k, right? It's G to the k. So then y is phi of G to the k. So y is in phi of G. It's in the image. So we're good. It's onto. Cool. 1-to-1. Fairly similar in terms of it's not too bad, right? So suppose x and y are in G, then x equals, say, G to the k, y equals G to the L. Or I guess we've been using I and j, right? So let's just do that. Alright, so G to the I, this is G to the j. And assume for 1-to-1, right, we assume that their images are the same. So phi of G to the I equals phi of G to the j. Well, what does this mean? So this means R to the I is R to the j. And again, this is where it's important that we're assuming this, right, that these powers are really in here, because I doesn't have to be equal to j. If you don't assume that, right, like 27, again, in order 20, would give you the same thing as 7. So I could have I be 27 and j be 7, and I is definitely not equal to j there. But if I restrict to the remainders, the ones that I really need, the ones that are distinct, then these must be equal, right? And so then I equals j, given that 0 is less than or equal to I and j is less than or equal to n minus 1. As long as we choose the distinct ones, then we're good here. And that's what we wanted, right? Because if I is equal to j, then it's definitely true that G to the I equals G to the j. So x equals y. And so we're 1-to-1. And then the last thing is that we need the homomorphic property. Right, so we'll let the x and y be the same as above, right? So G to the I and G to the j. So phi, fine. we'll just do this one. This would be phi to the g to the I, g to the j. But we can just rewrite this. And we would get r to the I plus j. But we can split this up, right? This is r to the I times r to the j. And so we can split them up via phi. And finally get phi of x times phi of y. And so this is satisfied as well. Okay, so the other ones are similar. Yeah, probably don't need to go into those. I mean, it's just the two elements in one element. It's pretty straightforward. All right. So I think it's worth talking about 428, and then the 429 isomorphism is super similar. You just no longer have to make the assumption that things are between like 0 and n minus 1 for your powers. But here, right, if we have a group with an infinite cyclic subgroup, then all of the powers are distinct, if and only if each g to the k is distinct. So one of these directions should be super easy. If for every integer you have a distinct element, well, the integers are infinite, right? So you definitely have an infinite group. So this direction should be pretty obvious, right? So z is infinite. So g has at least as many elements as the integers. Okay, so that direction is not bad. And it's really the other direction that requires a bit of work, although not too much, still not bad. So here, we assume this guy is infinite. Okay. And again, I think there was a hint on this one, right? So you should try to prove by contradiction. And you should have caught on by now that we continue to make this kind of same argument, right? So this contradiction, right, if you assume that they are not distinct, then you have a repeat. And then, so assume they are not all distinct. Then we have some repeats. So that just means that g to the I is g to the j for some integers I and j. But we've run this road before, right? Then we know we get some power that is the identity, right? So like without loss of generality, I is greater than j, say. It doesn't really matter. One of them is bigger than the other, and so we have some positive power that gets us the identity. But we proved this long ago. I think this is 417, right? So I minus j is a positive power that gets us to the identity, and therefore by 417 this guy is finite. But we assumed it's infinite, so this is a contradiction. Okay. So I mean, again, I just want to make it clear, like, we've used this assumption, right? This, like, assume there's a repeat, see what happens, I think 3 times in, like, 10 exercises. So, yeah, it's definitely something to keep in mind as a tool to use, okay, when dealing with cyclic things. Okay. All right, so 429, again, this is basically the same proof is 427. Except you leave out the assumption that k has to be between those certain numbers, right? Right, you just take that away because here we actually have distinct ones for all integer powers, but everything else is exactly the same. Okay? Questions before we talk about this modular arithmetic stuff? Because this is kind of what we're going to be talking about for a little bit, and these are super important examples of groups. I know not everyone has seen modular arithmetic, so I wanted to spend a little bit of time today, and then I may give like an extra practice worksheet for those who haven't seen it, because I know some have, some haven't. I'm going to give like a little extra practice worksheet and post solutions to that for like maybe before the next class. I have kind of an idea of what to do there. Okay, right, so, I mean, this is just a definition, okay, so Zn, now this is kind of an abusive notation, where I'm really just writing these numbers. It's really like equivalence classes of the numbers, where the equivalence relation is the thing that we will do in 432. That things are equivalent mod in if in divides I minus j. Essentially, you want to think of these as the possible remainders if you divide by n. And you can define an addition on these, right? So I'm just going to do like a random example. Let's do with like z6, right? So this is the stuff from 0 to 5, right? These are your possible remainders if you divide by 6. And so, sure, 2 plus 3 is 5, 1 plus 2 is 3, that's easy. But then, like, what's 3 plus 5? Well, that's 8, but 8's not in that list, right? And so 8 is the same thing. We would write this is 2 mod 6, and we use the triple bar here for its equivalent. And if you want to do that in LaTeX, it's literally \equiv for equivalent. And so this is what's called modular arithmetic, right? So like you're doing things, but only in terms of remainders. Some people call it clock arithmetic, right? Like you're going around a clock, and then every 12 you repeat. This is the same thing, right? Except your clock is basically like that cyclic Cayley graph, right? You went around 6 times, you went around once for 6, and then your 8 goes back around 2, and so you end up at 2. And so, if I'm talking about Z13 and I do like 8 plus 12, well, that's 20, which is equivalent to 7 mod 13. So I would say that 8 plus 12 equals 7 in Z13. Okay. Since we got a late start, I'm probably going to go like 2 minutes or so over here, since I know that lunch is after this and none of you have class. Okay, so then I just want to talk about UN briefly. So this one's not too bad, but you can also do multiplication, right? So let's again do Z13, but with multiplication. So I mean, it's the same thing. Actually, let's do Z10 because I want to make a point here. Okay, so with multiplication, I mean, you can do things like 3 times 4 is 12, which is 2 in Z10, right? It's remainder 2. And I mean, yeah, you still get a number when you multiply things. You can still talk about the remainder when you divide by your n. But here, unlike with addition, you don't have inverses, right? Because like with addition, I can do like 7 inverse is 6, since 7 plus 6 is 13, which is the same thing as 0, right? But in this case, like, what about 2? Well, the identity with multiplication, right? So, like, I mean, a times 1 is a, always. So that 1 is your identity for multiplication, as you would expect. But then, if I have 2, what's its inverse? I can't get to 1, right? 2 times anything is even. So we'll have even remainder when you divide by 10. So you can never get something like 1 mod 10, right? You can't get like 2 times an integer is 11, right? You have to have fractions. And so basically what the point is, and this is why we define UN this way, it's the numbers up through n minus 1, except for you only do the ones that share no common factor with n. So if I have z10, right, then u10 is going to be the things that share no common, right? 10 is 2 times 5. So basically anything that's divisible by 2 or divisible by 5 is thrown out, right? And so you're going to get 1, 3, skip 5, 7, and 9. Right? These are the only guys that share no common factor. And then this actually is a group, because once you have that, you actually can get an inverse in this case. And the reason for this is, so this will be the thing I close with. So this is a theorem. This is similar to the division algorithm where you should know it, but you don't need to prove it. So if the GCD of n and k is 1, then there exist integers x and y such that nx plus ky is 1. And so how do you get like k inverse? Well, this means ky is 1 minus nx. But again, in Zn, 1 minus nx is equal to 1, right? Because nx is divisible by n. So basically that would be 0. And so basically we're saying that ky is 1 in Zn. And so you have an inverse for k. It's going to be y or whatever y is equal to in Zn. So k inverse equals y here in UN. And so that's why we do this. All right. So I'm going to go ahead and end stream, I think. But if you want to hop on and ask questions in Discord for a few minutes, I'll be around for a little bit before I break for lunch. Okay?